Hello everyone and welcome to today's webinar, Harnessing the Power of Semi-EDA Standards, Implementation Best Practices. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You've joined the presentation listening using your computer speaker system by default. If you'd prefer to join over the telephone, just select phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the question pane of the control panel. You may send them in at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you'll receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce your presenters for today's webinar, Alan Weber and Ranjan Chatterjee.
Good morning or afternoon, depending on where you're connecting from, or maybe even middle of the night if you're in Asia. It's a pleasure to be hosting this event, follow up from last week's. We had great feedback on last week's event, and we hope this one will be as useful and meaningful to you as well. So let's get started. Again, today's webinar is about the implementation practices of the standards that we discussed last week. In particular, last week we talked a lot about the what and the why of the semi-EDA standards. This week we'll get into the how they can best be implemented, principally from the factory standpoint. There's of course a lot of work that goes into implementing this on the equipment, but that's a topic for another day. For those of you in the equipment industries, we'll probably have a webinar on that topic sometime soon, but we hope this will be interesting to you because you'll get to see what your customers have to do to implement this on the factory side. The topics we'll cover include some of the implications of the EDA concepts that you learned last week that affect factory design, some of the system technology trends that are driving modern factory system designs that are specifically pertinent now that maybe weren't 15 years ago when these systems were first developed. In particular, the gigafactory performance, reliability, and scalability requirements are quite daunting, and there are good ways of doing that now with commercial technology that we'll talk about. And that doesn't have to be a whole cloth thing. There can be a way of doing that with still being able to migrate from existing systems in a non-intrusive kind of way. So we'll touch on these topics today. Again, as with last week, we're not going to make you experts in any of them, but we hope to pique your interest so that if there's more you need to learn, you'll contact us and we can go even more deeply into this. All right, from an agenda standpoint, I'll start off with just a few slides repeated from last week, just to remind people what the sort of key concepts are that do impact factory architecture. And then I'll go specifically into those considerations as background for Ranjan Chatterjee's presentation, where he will talk about a cloud-native approach to addressing these specific requirements. And then we'll have 10 minutes or more at the end for Q&A. So get those questions ready and we'll be happy to address them. All right, so we'll start with a little bit of background again. For those of you that attended last week's, this will be a little bit of review, but won't go into near as much depth. As a reminder, the EDA standards are actually a suite of standards. 3 of them deal with the so-called equipment metadata model. That's the E120, 125, and 164 standards. This ladder diagram here shows how a factory client and a piece of equipment actually interact. But as you remember, you can have many clients talking to one equipment and many equipment talking to a single client. And so this picture is actually far more complex in a factory setting, but for simplicity, this shows how the two interact. E132 is the security standard, if you will, that makes sure that only authorized users can connect to the equipment. They have to know, of course, the URLs, the universal resource locators. You have to have those address strings, but you also have to have a client name in the access control list on the equipment in order to connect successfully. So once that connection is done, all subsequent communications between a client and equipment happen within the context of this session. A client may know nothing about the equipment other than its connection string, and so the first thing it would do is request the equipment metadata using the E125 services. Then the equipment would respond by sending the entire model over to the client. This tells the client system what is available in that equipment to be collected, monitored. That's really the only way you know what's in there. Now, unlike the GEM world, where the GEM manual is what contains all that information, the information about what's on the tool is actually resident on the tool. And that's actually a good feature because it's the sort of unambiguous version of what's there. Once you have that information, then the client can fashion any number of data collection plans, which are the specification of what the client is interested in on that equipment. Those plans are then downloaded and validated on the equipment side and stay resident there. Nothing, of course, happens until those data collection plans are activated. And once activated, the equipment is then responsible for monitoring the conditions specified in that plan and supplying the reports that correspond to those requests when those conditions are satisfied. So it's not a request reply kind of environment. You download your data collection spec, activate it, and then the equipment is responsible for providing the data when these conditions are satisfied. So, and this continues until that plan is deactivated and or the session is closed between the client and the equipment. So this is how all communication happens between factory systems and equipment in an EDA context. So I mentioned, I won't go into much depth here, but again, the model that's in the equipment is a hierarchical model. It contains a static portion on the left there, the E120, that's the structural part. E125 decorates that structure with all sorts of real-time dynamic information. That's also where the services are defined that allow you to request that model and interact with it. And there's a third standard, E164, that actually contains all the best practices from the first generations of implementation that explain what a good model is. Good meaning its structure, its content, its naming conventions, all of those things that make it possible to have very consistent implementations on the factory side. So again, the model is a really important concept with EDA, and the reason I mention that is it does have an impact on how you design factory systems. Of course, the other major concept is this data collection plan structure. This is a complicated structure that shows you the variety of demands you can place on the equipment. A data collection plan can have 0 or many of 3 different request types. Event requests, which allow you to specify a list of parameters that you want to see whenever a specific event occurs. A trace request, which also allows you to collect a set of parameters, but you do that according to some real-time interval in seconds. And you do that collection after a start trigger occurs until an end trigger or a stop trigger occurs. And you, again, collect that list of parameters during between those 2 events. Start and stop triggers, you can have multiple of those which are ANDed together. You can also have conditions on those triggers where you test the value of a parameter against some constant or other parameter. So this data structure has a lot of power, and it can be arbitrarily simple or complex depending on the application needs that you have. The third request type, of course, is the exception request, which corresponds to a GEM alarm, and that's something that goes bump in the night or some condition you want to know about. And you can filter those on their source ID, where in the tool they occur, the actual exception ID, or the severity. So these things in aggregate create these data collection plans, which again, you would define based on information available in the tool model, and then download, validate, and activate. So every time you see source ID in that data structure, that's referring to a location within the equipment. In fact, the source ID is the hierarchical name of those nodes on that left diagram. So it's a fully qualified name that gets you down to the leaf node of that structure. And the leaf on that structure is, of course, the event ID or the parameter name or the exception ID in that data structure. All right. So just as a quick poll question here, the EDA standards, of course, are far more complex than I can hope to cover in 4 slides. And we do offer formal training in this area if that's something that your company could use. So here's a question that says, have you participated in a formal EDA standards training session at some point in the past? And you can see yes, you have, or yes, but maybe it's been so long, the people have changed or forgotten all that, or no, and I don't know. So again, this is one way of making sure that people get to the same level of understanding as actually going through an EDA standards training, and those can be customized to be as short as a 3 or 4 hour session, or a day and a half if somebody is really getting into the implementation. Okay, so we see looks like we've got about half of our 60% of no's and I don't know. So there's fertile ground here for more education for those that are interested. So good to know. Thank you for your candor and addressing that question. All right, moving along. Just as a quick reminder, for those that are familiar with the GEM and GEM 300 standards that are the command and control standards for semiconductor factories, EDA does not replace these. The DA stands for data acquisition. You do not write information back to the equipment using the EDA standards. And so GEM, GEM 300, and EDA complement one another and together provide the totality of the command, control, and data collection functions that you need on equipment. All right, so let's move ahead to factory system architecture considerations. The system architecture, of course, is a complex document or a set of presentations that describe how systems are to be built in a given factory environment. We used to jokingly say that architecture is where the rubber meets the sky, but it is a far more serious topic than that and has to be considered in a strategic context. In particular, architectures have to support a company's manufacturing objectives, the automation capabilities that are slated for that facility, as well as general system requirements. And so all of these things can affect a system architecture, even just given the standards. Moreover, there may be system principles and constraints, either technical or financial, that affect an architecture. And then once those things are determined and written down, then that architecture can dictate what the company's development roadmap would be, which then sort of splits into sort of equipment automation topics, factory infrastructure topics, as well as manufacturing applications. And so the system architecture needs to cover all of those topics and how they are related together and how they behave in a production enterprise. So this is architecture, again, is a complex topic, and it's the reason we're focusing on this next set of requirements. All right, first and foremost, pardon me, let me get a sip of Perrier here. Okay, first and foremost, an architecture has to handle the functions that are required, and in an EDA context, there are a number of things to consider functionally in designing an architecture. Number one, of course, is knowing what the data collection requirements are for each equipment type. And, for simple equipment, that may be not that many parameters, not that fast. For complex equipment, you may be collecting hundreds or even thousands of parameters at high rates. And so this determines some of the requirements for the architecture to create pipes that are big enough to pass that data from equipment into the systems that consume them. Of course, performance management. The EDA standards have a whole set of performance management messages that the equipment generates in response to the operating conditions of the equipment, and so those need to be handled in a consistent way at the factory level. We mentioned briefly last week the notion of a freeze version. A freeze version is a set of the individual standards that are known to work together. The latest freeze now is Freeze 2, which is a specific set of standards. Freeze 3 development is underway. The standards community is defining what those are going to be, including a new infrastructure, but it'll be a few years before that is fully available in production. And so what you can imagine is that any given factory will probably have to support multiple freezes across the supplier base because the supplier's implementations aren't always in synchrony. Of course, adapting the IT policies for application and end user access. The EDA standards allow for a lot of autonomy on the data collection users, and that has to be done, of course, within some sort of set of guidelines, which have to be probably adapted from their current state. Managing data collection plans across a factory. Again, the plans are resident on the equipment, but gigafactories will have many instances of identical tools, and you don't want to be manually administering all of that information in that set of equipment. So automated tools for handling that are important. Deciding where and when to store the collected data. A lot of this data will be time series, very dense trace data, and there are repositories that are ideally suited for that kind of data versus relational data that other systems may generate and deal with. Of course, synchronizing timestamps across equipments and servers. This is important even with sort of good implementation of the time synchronization standards. This is still something that has to be managed actively because if you're merging data from multiple sources, knowing what time that was collected is vital in the use of that data. Of course, these systems are now mission critical. The biggest consumer of EDA data has been fault detection applications, and they are mission critical. And so the piping that provides that data from the equipment to the systems needs to recognize that and support fault tolerance. And that can be a tricky thing to implement if it's not thought about ahead of time. And then finally, all of these things need good operational support tools to keep running in a production gigafactory environment. All right, what can sometimes impact things even more than the functional requirements are the non-functional requirements. And these are what are sometimes called the ilities: the scalability, availability, flexibility. Performance is an outlier, but all of these things have to be considered when designing an architecture, because what worked for, let's say, 3 or 4 pieces of equipment and 100 parameters will not work with 3,000 pieces of equipment and potentially millions of parameters in that environment. And so being able to handle the massive scale of modern factories is important. Performance, reliability, availability, all of these things are important and impact architecture design. Flexibility and extensibility are sort of two sides of the same coin. These systems all change over time, but they need to do that seamlessly while production is occurring. And so this provides another set of constraints. And finally, of course, ease of use. So taken together, the functional and non-functional requirements go into the sort of architect's tool bag, if you will, of things to address. All right, what the next few slides I'll present are kind of a set of components that we've sort of imagined that would exist in an EDA factory system. There's no one commercial system that has all of these in exactly the form I described, but it is a way of taking these requirements and grouping them according to function. So as you're thinking about how to accommodate, let's say, a few thousand pieces of EDA-enabled equipment, how you would do that. First of all, so this is a list that I'll cover a couple of them briefly here. And again, this list incorporates lessons learned from multiple EDA implementations across 10 or more years. We're familiar with how the standard has evolved, both as a standard itself and how it's been implemented in the equipment and the factories. And so this is sort of a snapshot of the lessons learned from that experience. First of all, model manager, this is, again, we've said that the models are resident on the equipment. And that's, again, where they live in a production environment. But if you've got 2,000 pieces of equipment, a lot of those may be identical, some of those may be different. And you're going to want to know, let's say, what those differences are, and perhaps be able to analyze these models offline rather than from the always being connected to the equipment. And so being able to actually know what version of what model exists in every piece of equipment is important. Maintaining a directory of that, being able to manage those models, make sure that when somebody maybe has inadvertently changed one. The other issue, of course, may be you may have naming conventions in your factory that don't exactly align with how an equipment supplier has named their model. And so there may be a mapping layer in your system where you impose some sort of company-specific or factory-specific naming convention. And of course, those mappings will need to be maintained somewhere where they can be aligned with the source models. You may be doing a lot of sort of checking. You may have a template of a model that you would use to develop application software, but you might have to tweak that depending on which equipment you're actually connected to. And so being able to generate instances from the templates is important. And then, of course, I mentioned version control and monitoring modification, either accidental or not. All right, a plan manager. Now, again, data collection plans may be created on the client side, but they're stored on the equipment. And if you have, let's say you've connected to a piece of equipment and created the models you need for the DCPs that you need for the applications you're supporting, you don't want to have to go to each one of potentially 50 units of equipment and create those models individually. You would a lot rather, upload those, check to see where the compatibilities are among the metadata models in that equipment, and then modify and download those data collection plans automatically if possible. Of course, another version of that is normally you have to be connected to the equipment in order to validate that a DCP you've created is correct for that equipment, because the source IDs that you refer to have to exist in that model for that DCP to work. Well, doing that online with production equipment, can be a constraint, and so being able to do offline DCP development with a copy of the model is important. And so this is one of the features that a plan manager would support, a full set of create, copy, edit, delete functions for DCPs, even when not connected to the equipment. Of course, you would need the final say would be downloading and validating that to an equipment, but you could do most of that work offline if you needed to. A plan manager could actually use a copy of a model to automatically generate DCPs for some kind of purposes. For example, the initial discovery of equipment and process behavior, a lot of this could be done by automatically parsing an equipment model and generating data collection plans that activated the various events and observed the behavior. That doesn't all have to be done manually. Another important function, of course, is knowing what impact a data collection plan is going to have on the equipment's behavior, so that if you have, let's say, 5 active clients that are all collecting data from the tool, you want to make sure you don't push the tool beyond its performance threshold. So knowing where those thresholds are, either by documentation or experimentation, you could calculate a demand profile per data collection plan on that equipment, making some assumptions about what percentage of the time it ran, and make sure ahead of time that you weren't activating too much data collection activity, for a given piece of equipment. And of course, the other side of that issue is knowing what the priority scheme among the data collection plans is, because if you start to run into a performance threshold, you don't want the equipment automatically disabling all of your DCPs. It would make more sense to deactivate those according to some priority scheme. But a lot of this, again, has to be thought of ahead of time because the standard itself is silent on how that process works. All right, a couple of other components here. Of course, equipment connectors. Ranjan is going to talk a little bit more about this in the next segment, but providing a simple API to all of these services for the applications that run on the factory system is a key function here. It can even unify the interaction with the equipment if you have independent multiple standards implemented on your data sources. So EDA is only one data source, of course, we're talking about today, but there are others that could be unified under a single equipment API. So this hides some of the unneeded complexity in the application, and the equipment connector may be a place where equipment models can be cached. Also, when you initially connect to a piece of equipment, you have to upload that model. That process can take a lot of time and can be cached if you know it hasn't changed. Of course, managing the whole life cycle of sessions and DCPs has to happen somewhere. This is all the domain of the connector, in addition to its normal data report capture functions and timestamp adjustments. All right, a performance monitor. This is another function that you've got here. Watching the EDA activity across the network is important because, again, this is mission critical stuff. And so being able to know in a single place, what sessions are active with what equipment, what DCPs are active, what clients are, being able to look at in aggregate the demand on your factory equipment and having that be somewhere that you can get to is an important function. This is something you don't think of when you're worrying about one or two pieces of equipment, but talking to 3,000 pieces, that's an issue. Of course, monitoring these performance thresholds and being able to generate notification events to stakeholders that want to know about that, and then using the DCP priority scheme to deactivate and reactivate those as the performance changes. This is an important function. And then finally, looking at the sort of usage statistics and tracking that over time. And of course, finally, an administrator toolkit doing all of this, with the software talking to one equipment, that's one thing. Talking to 2,000 pieces of equipment, you really need good tools to do that. And so all of the functions, all the configuration functions that pertain to different implementations of the EDA standards on the equipment you want to have somewhere. And so that's what the administrator toolkit's all about. And it's really a sort of a catch-all for a lot of the other functions that you have. All right, the final slide here is one that Jack Downey would have presented last week had he not been assaulted by a production problem. And I wanted to use this slide to show what, let's say 10 years ago, an advanced factory system architecture would look like. It's one where you have a non-intrusive implementation of EDA in parallel to the GEM 300 implementation. EI in this picture stands for equipment integration. You'll see that the GEM connection has a separate network than the EDA connection, and the only sort of link between these two are some messages that went back and forth between the GEM EIs and the EDA to provide context data in cases where the equipment didn't provide it. But you can see here that all of that was supported by a set of factory level admin functions that had its own configuration database, as well as a time series database that supported the sort of real-time nature of a lot of the data that was collected. Well, this is what was a state-of-the-art architecture 10 years ago. Now, of course, if you were starting this job, you would probably do it with a whole set of new technologies, cloud-based technologies that are inherently scalable, inherently reliable, and for mission-critical systems, this is how you would look at it today. And so with that, I'm going to pass it on to Ranjan Chatterjee, our Smart Factory Business Unit VP, who's in charge of those architectures and systems to do just that. So Ranjan, take it away.
Yeah, Hi, everybody. Thank you. So what I'm going to talk about is the other side of the pipe, right? So this is basically on you have the equipment side, which Alan covered quite a bit, and then a bit of the on the other side of the pipe, where how you collect the data, how you process the data, and then how you present it to other applications that would eventually visualize the data. So if I, yeah. So the part that you want to do is you want to do it in an abstraction layer where it's a platform where you can deal with the volume and the variety and velocity of data that EDA enables, right? So that's the key to what I'm going to talk about now. So if you look at it, the platform enables you to, if you look at the picture on the left, this is from McKinsey, where they tried to see how would you use, what kind of architectures would be useful or required for actually gathering and harnessing the ability of data that EDA and other protocols enable. And the architecture that is used in most fabs and factories in the world is one on the left, right? So you have individual tools collected to the equipment, and then the applications, they are not totally integrated. The one on the right is an integration layer that talks to all the machines, irrespective of the protocols, collects the data, and then presents it to the application layer in a unified manner, right? So you have unified, universal accessibility for connectivity, as well as for doing things like machine learning and AI, you have access to data across all the tools. So if you want to do that, so the key thing that most people would see is what's above this whole iceberg, right? So which is the factory and mobile applications. But what you really need underneath it to actually make some head or tail out of your investments is the data platform, which can have this pub sub means publish and subscribe. You have the ability to stream data, you have security, you have support for multiple protocols. And like what Alan suggested is you have EDA to get the high speed data, but you still need something else to do the control, which is what used in semiconductor factories. Like they use GEM to do control of the machine. So once you have the data and you make some you make some decisions, then you want to implement those decisions. So this enables having a data platform that can actually collect data from the high-speed data sources like EDA to send it to applications is a very important part to free the developers from the nuances and complexities of implementing multiple protocols. So how would you do that, right? So one is the protocol itself. We have covered that in detail with EDA, so I'll skip that part. The second is the technology, right? So one thing that you would want to do now is make it cloud and mobile enabled, right? And what does that mean, and how would you benefit from it? This is the universal accessibility, where you can actually access the data from anywhere in the world. In this COVID times, that's a very important thing. You want to be home and you can still get data from the factory. You want to be able to deploy things in a very quick and easy way, and then be able to support a factory from different things, right? You can support a factory in US from Taiwan, or vice versa, right? So you because nowadays having the talent to do a lot of these things is also a very scarce resource. So you want to use them wherever you find them. So the second part of this technology is the ability to scale. And this is where the containers come in. And we don't have as much time today to discuss this in detail, but the ability to containerize and the ability to deploy containers in a factory enables you to scale them both horizontally and vertically. It's a really important thing. And that enables you to actually deploy technology that can be monitored across the whole world. So we have customers that are sitting in California that are monitoring their factories in China in real time. So the question is, what would this platform look like? So this is the representation of what it could look like. The bottommost layer is where the machines are. They will talk multiple languages or protocols. In this case, of course, we are talking about EDA, which enables high-speed data, but then it works in conjunction with technology or protocols that are already there, like SexGEM, which enables you to do control. And then you may have other protocols that do Kafka or MQTTs for some kind of discrete sensors. So you want to collect all this data, present it to the applications in a meaningful. So what we are doing here is, what we are showing here is a RESTful API that can then feed the data into various applications. The applications can be from companies like us. It can be applications that you have developed that within your own IT organization, as well as you may have partnered with others for best of breed applications. This enables you to do that. And then the final thing on the right says actionable insight. So you can actually go and implement that using various protocols, and EDA being the primary one for collecting the data. So how would this get deployed, right? So one of the poll questions is, we want to know, like, are you thinking of this, right? Would this kind of an architecture and the ability to access data from mobile phones or wherever, any mobile technologies, is this something that you are thinking of implementing in your manufacturing systems in the future? It's a really, it is ubiquitous in all kinds of places, but not as much in manufacturing right now. And we're interested to understand if that's something that you are thinking of doing. These technologies are getting implemented more and more, where the factories would look more like a data center, but it also has implications on, of course, security and accessibility. So okay, well, that's very interesting. It's not very surprising, but it's very interesting that it's actually, there's a lot of aspects to this, deploying this technology, that probably makes it into the I'm not sure category. um, so let me go to the next. So actually, it's interesting from the poll, like the part about what makes people not too sure is how would this work in a deployment. So what I showed you is the architecture of a system, but how would it look like when you deploy? Most factories now can deploy a cloud-based architecture on premises, which means that most of the data never leaves the factory floor. So you can actually use a modern architecture, but it doesn't have to be all on AWS or Azure or Google Cloud or your own thing. It can all be inside. So that's a very key part, right? That should make it more secure and make it more controllable, and you and your customers can actually be able to use all the IT resources you have to keep data within the four walls, right? So that's definitely one option, and we support that within PDF and Symmetrics, and of course, a lot of other deployments are working this way now. The other option is where you can actually do like a hybrid deployment. What that means is that you collect a lot of the data within the factory floor, and it stays within the factory floor. So the raw data stays and never leaves your factory floor. However, you can have calculated results from various analytics that you have done that are stored on the cloud, right? And that is accessible to anybody. So if you are in an airport and you want to look at some charts and graphs that use calculated results, you could do that. You don't really need access to the raw data, and that is always secure, and that behind your own firewalls and the four walls. So that's another option that I think is a very popular option. We have a lot of customers that want that and that we have deployed that actually use this option too. So we have a lot that are within the prem, like an on-prem, and some that are on hybrid. Why is this option very popular, right? One of the reasons is, if you look at the box on the left, you have your application, you have your OS, you have a server. It is hard to orchestrate and scale this kind of thing. So if you have like 1,000 machines collecting data at 10 hertz, and you have so much data coming in like EDA enables, then how do you make sure that you don't have one point of failure, or how do you manage this? So this is where you have this orchestration. This is a technology called Kubernetes that allows you to horizontally scale. You can do load balancing, you can do health checks, and it lets you do this scaling seamlessly. And you can do that without putting too much cost into it. So of course, you can use things like Amazon and Google and Azure, but you can also do it private cloud, right? So you can actually deploy it in like OKD or various other open source tools allow you to do these kind of orchestrations. And then finally, if you're able to do this, then you can actually go to something what people call nowadays serverless, right? So it's hard to manage a server. It is probably harder to manage more than one, but the key is where you have it on-prem and you have these containers, and then things like Kubernetes do all this scaling seamlessly behind the scene. So you never have to manage a server, which is called, so the best server to manage will be no server, right? So that's kind of where I think people would be going. This is how data centers are run nowadays. And as the factory generates more and more data, as you heard from Alan, and we are orchestrating as well as instrumenting all the machines to generate all this data, then we will have to figure out a way to consume all this data in a meaningful, inexpensive, scalable fashion. And that's what these kind of platform technologies allow. So that concludes my part of this, and thank you.
Okay, thank you. Thank you, Ranjan. Cheyenne, it's back to you, I believe.
Thank you both so much. So we're now going to begin answering the questions submitted during today's presentation. As a reminder, you can still submit questions through the question pane in your attendee control panel. So Alan, it looks like our first question is for you. Do you have to be connected to a piece of equipment to develop its data collection plan, DCPs? If not, how can you check their validity?
Oh, okay, thank you. Yeah, I touched on that just briefly in that in the part on the model manager and the plan manager, but normally, yes, but if you create, let's say, an offline tool, pardon me, a software tool that has access to the model, then you could actually use that model to validate that all of the source ID and event IDs and parameter IDs existed there, and that was valid. You would probably, be 95% certain that the data collection plan was accurate. Of course, the final authority is the tool itself. And so there's a E134 service called Define Plan, and you send that service with the XML for the plan to the equipment, and it comes back with, yes, that was great, or it comes back with a list of errors if it was not. And so the answer is yes, you can do that. It takes a little bit of trouble. You have to have the model resident, you have to have uploaded the model into some tool and know how to use it to do that. But that is a function worth doing, because you can't always guarantee as you're developing DCPs that you would have ready access to a production tool. So good question, thank you.
Great, thanks, Alan. And we actually have another one for you. How much data does a factory system typically need to collect from an EDA-enabled process equipment?
Cool. Okay, that heavily depends on the complexity of the equipment and the nature of the application that needs that data. Let's say if, a typical use case, of course, is fault detection and classification. If you had a sort of moderately complex tool, you might be collecting 200 or 300 parameters at 1 to 5 hertz. And you would put those into multivariate models and evaluate them in real time and see what the answer came back. If you are, let's say, a 18-chamber litho track, and you're monitoring all of its behavior, you may be collecting a couple of thousand parameters at 1 hertz and running those kind of models. And so, and if you're collecting very dense data for machine learning apps and offline sort of applications, you might be collecting, let's say, a couple of thousand parameters at 10 to 20 hertz. So you could get up to 40,000 to 50,000 points a second, or samples a second, for a really complex tool. So it varies a lot depending on the application, but anywhere from a few hundred per second to many thousands. And of course, you multiply that by the number of tool instances at that time. You're talking about terabytes a day.
Thank you. And so, Rajan, our next question is for you. Are cloud-based systems being developed to handle the scalability and availability requirements of mission-critical applications like EDA data collection?
Yes, that's right. We are working with a few customers. They're big foundries that are doing that. So, because EDA inherently enables you to collect a lot of data, various types of data at like what Alan said, like 10 hertz or more. So, you need a system like what I just talked about to do that, and people are doing that. The one is, of course, the ability to scale and consume this data. The other is the availability. You want these to be fed to modern applications like that allow mobility, where you can access the data from anywhere securely, right? So that is another reason why this is driving, both because it is faster, better, cheaper, but also more accessible, right? So these aspects are driving this investment in these platform and cloud native applications and technologies.
Let me just
Thank
add
you.
one thing, which is a departure. 5 years ago, if you asked a number of the leading chip makers if they would ever put their manufacturing data in a cloud, the answer would have come back absolutely not. But with the security improvements and the benefits Ranjan just talked about in terms of reliability and scalability and portability, those benefits outweigh what used to be the concerns on the security part. So these are getting addressed now.
Thank you. We have another question, Alan. I believe you touched on. We're starting to hear about a Freeze 3 version of the EDA standards. When will this be complete and available from the equipment suppliers?
Okay, yeah, we actually got this question last week. I noticed in the aftermath and didn't get around to it, so I'm glad somebody asked it again. Freeze 3 has been underway, the work on that in the standards community for the past couple of years. It will include a lot of minor changes to all of the EDA standards, but a couple of major changes to the underlying infrastructure. So the SOAP XML infrastructure will be replaced by gRPC protocol buffers, which is a binary protocol rather than a text space and inherently faster. A number of companies have benchmarked this and show anywhere from 10 to 20x improvement in sort of raw data collection performance. So there are other sort of features that will allow caching of high density data in a way that can move it more quickly, as well as a number of ease of use features. So there's a lot of compelling work going into Freeze 3, but things take time, and those ballots are still being created, worked on, and passed through the community. Some of them have passed, but it'll be probably at least a year and a half or two before that is through the entire standardization process. And of course, that means the equipment suppliers and factory system people have to then adopt that and test it and use it. So my guess is it'll be probably 3 years before there starts to be production equipment with full implementations of those. But there are good reasons to start that early and now, and we're prototyping some of those features which could accelerate this significantly. So the sort of easy answer is anywhere from 1 to 3 years, but their changes are significant enough to where it's worth starting now to understand those technologies and how they can impact EDA implementations going forward.
Thank you. So our next question, what are implications if both GIM and EDA are used to collect data from the equipment?
Can you read that again? I'm not quite sure I fully understood the question.
Absolutely. So what are the implications if both GIM and EDA are used to collect data from the equipment?
Okay. When I guess the key word in there is both. One of the EDA standards, the E164 in particular, says that any information available on the GIM port should also be available on the EDA port. That is not always strictly followed, but that is a design requirement. And moreover, they should be available at exactly the same time with the same timestamp. So it shouldn't matter, which interface is used to collect that data. The probably practical answer is that you probably should put it on whichever port the application that you are using gets its principal information. So if it's a control application that is needing information to make a decision and then change a recipe parameter or a setting or something else, then the gem port is probably the right place to do that particular data collection, unless of course the information is voluminous enough to where you would want to use the EDA port for it. Again, it also depends on how tightly connected the data collection devices are in your factory system. If the gem data collection hosts or clients are physically and logically very distinct from the EDA ones, it may not be that easy to synchronize the two together. On the other hand, if you have a platform like Ranjan just described, where the only difference might be at the connector layer, and the instant you're beyond the connector, you're into a sort of seamless integration platform, then it wouldn't really matter, and you could collect the data the most convenient way, and it would be available to that application, and then the answer could be routed back through a gem port to the equipment. So it really depends on the architecture of the client systems and the applications that are consuming that data and what function is needed once that's consumed. If it's a control function, then of course you need to have a gem pathway back to the equipment to use it. So kind of a long-winded answer, but it's not an easy question actually. Thank you.
Ranjan, you might be muted.
So in a nutshell, though, I think in most places they both coexist. Like what Alan said, I mean, you collect the data, you have high-speed data coming through EDA, and then you want to use it to do some actionable insight. Then you use the gem port to control the equipment, right? So you may actually have both, and most people do, right? So.
Perfect, thank you. How do you see the feasibility of closed loop systems? For example, feedback from apps processing EDA data back into controlling the equipment.
I think I answered that question before it got asked. So that's kind of exactly what I just said is you would collect the data, you would do the analytics, and EDA would be a very good way to do high-speed data. And then once you have that, you want to do some actionable insight, you want to send some control things, then you can use GEM to do that. So this will work pretty seamlessly, and it works now. I mean, they're both meant to coexist, and they work really well together. So you can use the investment you did before and then enhance it with EDA.
Thank you. Can the data platform layer be used without the EDA platform?
The platform layer is, it is a vehicle for implementing various protocols. So it can be used without EDA, it can be used with EDA, it can be used with GEM, right? So the benefit of using a platform-based approach to doing this kind of connectivity is that you can do EDA, GEM, a whole bunch of other things. So there is no need to exclude anything. You can actually think of it as a more of an inclusion thing, right? So you can actually add more protocols in future without having to worry. Right now, most monolithic architectures, you may have to see how, when you add another protocol, how it affects the rest of the implementation. In a platform-based approach like I just described, you don't have to make that choice. All the investments that you are making, you just keep adding on top of it. A good analogy would be like how cell phones are now. I mean, you have GSM, CDMA, TDMA. It has multiple protocols, but nobody knows, right? And in the past, like 15 years back, you had to know which phone and which protocol. And I think a lot of that is what exists in the factory today. And what would be in the future is you may not even care, right? Everything will coexist, and you can add new protocols if that's what makes sense for a particular application.
Yeah, I think that another aspect of the platform is on the north side of it. A platform like that enables an ecosystem of application providers, sort of unfettered access to whatever data is piped into it. And so the cell phone analogy is another good one. The Android and iOS devices support a very broad set of applications from hundreds of suppliers. And so not only does it harmonize the different protocols on the south end, but also opens up the world to a whole commercial ecosystem of providers on the north side.
Perfect. So our final question today, how common is the use of SSL in factory implementations of EDA?
Um, Great question. Not common at all. I think one of the early design requirements for EDA was that it enable sort of remote access. And so people said we need to support HTTPS and SSL in order to do that securely. To date, I know of no factory that's actually deployed that version, because they keep the EDA portion of it inside the four walls. And that is possible even with the hybrid approach that Ranjan showed. If you still chose to use a non-SSL implementation, you could put that on the connector layer and still have the benefits of a hybrid or cloud-based solution for the rest of it. But the SSL was not, that turns out not to have been a big requirement, because people have kept this inside the factory walls. So.
Great, thank you. Thank you, Alan and Rajan, for presenting today, and thank you everyone for attending today's webinar, Harnessing the Power of SIMI EDA Standards Implementation Best Practices. If you have any other questions, please email them to marketingmanager@symmetrix.com. Once you leave today's webinar, you'll receive a survey on the presentation, and we would appreciate it if you would complete that feedback. You will also receive a follow-up email within 48 hours with a link to view the recording. On behalf of Symmetrix and our guest presenters, thank you for joining us today, and have a great rest of your day.
Thank you. All right.